Okay, good morning. Thank you for your assistance, and of course, thank you very much to the organization to invite us to present you the photonic manufacturing processes at IMB-CNM. I made to fabricate photonic components. Let me see if I know how to work with this. Okay, we'll present you first the outline that we are going to speak with. We start with some overview of the different photonics technology. Then we will speak about the technological roadmap that aboard EMV and VLC. Then I will detail use some technological manufacturing processes. And finally, I give you some results of the project. Regarding to the photonics technology, okay, you can see on this slide some of the main photonic integrated circuits based materials. All of them are very important and has been developed in many years, but the most important one, or the most developed one, has been the silicon circuits based on silicon on wafer, on insulator wafer developed. Another technology that has been anytime more interested on, people are interested on this technology, is the silicon-based dielectric technology, based on nitride silicon or oxide silicon. And I try to explain you why we are interested on that technology. Next slide, we see a comparative table of both technologies. So both technologies are very similar because both comes from microelectronics technology. So, for example, in terms of CMOS compatible, they are very similar. But if we detail some other characteristics, we can see some difference. For example, the substrate of the silicon photonic technology is based on silicon on wafer insulator. But in silicon-nitride technology, the substrates are based on silicon or glacis wafers. So those wafers are cheaper and easier to work with. If we look at the contrast or the monolithical integration, silicon photonic has better characteristics as silicon-nitride technology. But if we look for the propagation losses, we see that the scattering and birefrequency characteristics are higher in the silicon technology and due to the crystals of the silicon. So silicon-nitride technology is better looking at these characteristics. Also, if you see the source integration and, of course, the wavelength range is higher in the case of silicon-nitride technology. So, due to those characteristics, we try to get the silicon-nitride technology. I will explain you more or less how is the work that to abort this roadmap. What do we need if we want to fabricate photoelectronics components? So, of course, we need a clean room. But this clean room has to have developed process to be able to fabricate or to make good components For do these processes, we need, of course, expert personnel, engineers, and very training personnel doing the test, also the fabrication. It's like I call here experts. And also you need the software to make your design with the characteristics that you want. Sometimes this software also has licensing, you have to get them. So if you have all of these group of needs, then you enter in the cycle of test, of design, fabrication, and test those devices. So then you design, fabricate, and test, and then you go in a cycle redesigning and retesting to get your correct device. How can you get a clean room? So you have two options. You can make your own facility, so make a clean room, contract experts or train them, or you can use an open foundry. So a foundry a foundry where you have experts and can make for you the photonic circuit. So, of course, make your own facility is very expensive because, you have to make the clean room, the expert, and so on. And if you use an open foundry, then you have just to pay for the fabrication or the engineers. So the cost and time consumable it's affordable. But how can we reduce a little bit more this cost and time consuming? So you can enter in a multi-project wafer, okay? In a multi-project wafer, you use a software which is developed and tested by design experts, and this software has been tested and fabricated in a foundry who knows very well this software. So that reduces a lot the design cycles because it has been tested, designed, fabricated, tested a lot of times, and the fabrication is it's almost ready to fabricate the device. Of course, you avoid licensing cost, and I think we think that is the way to get reduced costs. So, for all of that reason, I'm sorry. I'm sorry. For this reason, VLC Photonics and IMB-CNM have developed a fabrication process based on silicon-nitride technology with a design library in a multi-project wafer. So the process technical features, as you have seen in the past slide, the wavelength is very wide. It's from visible to my red. We are working with 3 waveguides, cross-section, which we call the shallow, deep, and mini-deep. We also can fabricate thermo-optic tuners that could modulate the wavelength. And also, we are ready to open some areas in the waveguides to make some sensor, for example. And you can see on this slide the different blocks developed on this technology. Also, some photos of the different circuits fabricated. So the foundry that we propose to fabricate these components are seated in the Instituto of Microelectronics of Barcelona, which is the Barcelona place for the Centre Nacional of Microelectronics. It belongs to the Spanish Council Center, CSIC, and it has a clean room called, it's a large facility called integrated, a micro and nano fabrication clean room. And some numbers of the institute is, for example, the budget of the 2015 year, it's 10 million of euros. And the percentage of external funding and the different sources of these projects. The personnel who works in the CNM in this year were 190 people. Now I think we are almost 190. And our interest, which is the clean room people, are 39 persons, 24 technicians. Okay, I'm sorry, 39 for the clean room, and the technicians, which are for the maintenance of the installation. The clean room has 2 laboratories. The main one is 1,500 square meters, and we have a small one dedicated to the bonding, special bonding process, which is just 40 square meters. So now I'm going to talk about the technology and manufacturing processes to make these photonic integration circuits. So starting with a silicon wafer, we work with 100 millimeters wafer, 500 bulk of silicon. We grow with a thermal process. Okay, I'm sorry. We grow thermal oxide, which is the substrate for the white, and we deposit LFCVD silicon-nitride, which will be the white, and then with 2 different photolithographies, we define the 3 different waveguides, the 150 and 300 nanometers waveguide. Once the guides has been defined, we cover them and protect them with the cladding protection, which is a PCVD oxide, silicon oxide. And then we have now that we call basic structure. So adding to this basic structure, we open some areas, which I say before, to make some sensor or just have the guide in the air. And also we can pattern on the wafer some thermoheaters by a technique of lift-off technique that I will explain now. So some technological parameters, if we see the design dimensions, we can see the different default and minimum values of the deep waveguide, the shallow waveguide, and also for the range of the heater. So those values are in the cycle of test. So we propose, we test, fabricate, and then we can modify those values, okay? And regarding the layer structure that has been changing in the different multi-project wafer that we have done. We start, for example, the substrate, the thermal silicon oxide, we start with 1.5 micron, and our target is put 3 micron. Until now, we work with 2.5, is the biggest one we fabricate. For the cladding, we start with 0.5 micron, and now we get to 2 microns of cladding oxide. And the thermoheaters, for example, we have not still decided which layer it's better to deposit on our structure because the definition process, the bonding, and the resistance for the metal on the wafer is a compromise, so we haven't still decided which one is better to process and to fabricate the circuits. So now I'm going to explain you some details about the different process, but it will just a resume. I won't go ahead to them. So, but okay, if you have any question, I can answer you. Okay, we start with we call thermal oxidation. The thermal oxidation is a way to produce silicon oxide on a silicon wafer. So we put the wafers in a furniture, 120, more than 1,000 degrees, and we put an oxidizing agent that could be oxygen or water, and with this temperature, this oxidizing agent goes through the silicon and oxidize the wafer. So I'll show you also the table with the different values with the target in the different multi-project wafer that we fabricated. So you see that it's a very homogeneous process, and it's also very repetitive. Another process to grow a layer is the LPCVD process, which is to grow the silicon-nitride layer. Use it for the shallow and deep waveguide layer. So this process, like its name, is low pressure chemical vapor deposition. So you flow two gases, in this case two gases, into the chamber and submit it to the low pressure, and then they react, and then will form the silicon nitride and is deposited on the surface of the wafer. So this technique gives us a problem, which is the content of hydrogen on the layer is very high. It's almost 80% of hydrogen. So it could produce some losses and also some stress that also produce, again, losses in the propagation of the light. So again, the table that you can see also the values are very, very repetitive and homogeneous. So it's a process very, very well established. So next process I am talking about is the PCVD deposition. It's used to the cladding protection. And again, it's a chemical vapor deposition, but now it's not let me find the word. The motor is not the low pressure. The motor is the plasma. It's plasma enhanced. So we submit the gases to a radio frequency, who makes some ions. Then the ions react, and it's deposited the layer desired. In this case, is silicon oxide. I'm sorry. Okay. So again, a table showing you the different values for the different projects. So in this case, you see that the values are not as homogeneous and as the processes that we showed you before, but still they are very, very good processes. Okay, the last process to get the layer that we need to fabricate the photonic integration circuit is the evaporation of the metal to fabricate the thermoheaters. It's a very similar system, but in this case, the high vacuum makes possible to evaporate directly the metal, which is not on any component, it's the metal that we want to deposit. It evaporates and it goes through the chamber until the substrate, and then it will is deposited in the substrate, the silicon wafer. Okay, again, it's a very, very high uniformity process, also for the sub-nanometers values. So we can get, for example, if we want 10.5 nanometers layer. So it's a very nice process. But still, we have some problems on deciding which layer is better. And again, I want to say you which is we will define which is the better for the lift-off process, which is the process used to define the resistance on the layer on the substrate. I'm sorry, and the bonding process. So once all the deposition or the different processes to grow the layers has been, okay, I'll show you. Now I'm going to explain you about how to pattern the design onto the wafer. Okay, so we pattern the design with we call the photolithography step. So the photolithography step consists on put a layer of resist, which is a chemical component which modify its structure with the light. So we pass the light. Okay. Okay, we pass the light through a mask, which has the draw, the designed draw, and the light who pass and react with the photoresist change its composition. So then we remove the part of the resist that has been chemical changed. We use a type of photolithography that we call the stepper, because we use a stepper equipment, which is a special equipment who reduce the reticle or the design that we draw 5 times to the value that we want. So with this type of photolithography, we can get lower dimensions than the standard lithography. So you see that we can get 400 nanometers and with alignment, nice alignment, which is 100 nanometers. So we use 3 different photoresists for the 3 different etching steps. So that you see also that not only the stepper or the equipment that we use to make the photolithography, but also the photoresist that we use to make the process also define the dimension that we are going to draw. So the different processes has different minimum dimensions. Also remember in the table that we show you the dimensions for the technological dimensions are bigger than these values because the technological values are made by the mixture of the photolithography and etching steps. So we can get this dimension with the photolithography, but when we process and etch the layer, the dimension also could change. So some images of the devices that we fabricated. Okay, our stepper is able to draw a maximum chip, which is 22 plus 22 millimeters. So we can draw 8 chips per wafer with this size at the 100 millimeters wafer that we work. So we divide this chip in 4 large areas and 8 medium areas that could be from different partners. We normally get 20 dies per user. So an schema of the numbers that I told to you, and where you can see how the wafer draw and how the chip is drawn in or pattern in the wafer. So again, that we saw, we told you in the past slide. It can allow us to share the cost of the fabrication. So I'm going to explain you a little bit about the process to remove the exceeded layer once has been deposited and photolithographed. So we have 3 different techniques. One of them is the reactive ion etching. It is used to eliminate the non-photoresist protected and to design the wave guides and the trenches. So the process consists of, in a chamber, we put some reactive gases, which and the radio frequency makes a plasma, and those gases are able to react with the layer which is not covered by the photoresist. So you can remove all the exceeded layer that you have not want on the wafer. So on the slide you can see the 2 different processes for the 2 different etching, and one characteristic which have this, and this process is very anisotropic, and it's very, very nice to have a good control of dimension. So you can see in this FIP cross-section how we can get a very, very well-defined waveguides. Another process we use to define the pattern on the wafer is the wet etching. It is used to finalize the cladding layer trench formation. Why? Because we have to, we want to avoid the damage on the deep and shallow waveguides. So you put in a bath the wafers and etch the silicon oxide with a buffered oxide etch, a commercial etch. And then you arrive to the waveguides, and the waveguides are okay. We won't damage them. So the good selectivity is that we make able to open some areas. If you've seen, I don't know if it's very clear, but you can see on the middle of the waveguides a square, which is the open area where you see the waveguide like, okay, there is no problem for it. And the last process we call about is the lift-off process. Is the process to define the metal thermoheaters. And the lift-off process works a little bit different like the other process because it's an additive process, not a subtractive one. So you put first the photoresist, then you put the metal on top, then you remove the photoresist, and then you have the draw on the wafer. Okay, and again, you have to consider three items in the lift-off process. You need a metal with good adhesion to the wafer. You need that the thickness be less than 300 nanometers because you have to get enough place for the solvent to go through the photoresist and remove it. And you need a negative profile to avoid some defects that I will show you on those photographs. So if you see, the first one is a very good lift-off process, that you see the profile very nice. And the second image is a lift-off process which has some problems, and okay, it's very clear. Okay, so finally, I will give you some results obtained on the different fabrication. Okay, until now, the thing that we are looking for are the losses. So we can divide them in two different losses: the in and out coupling losses and the propagation ones. So regarding to in and out coupling losses, we have to be careful with the end facets. We have to be careful in the distance and the geometry, of course. So if you look at the end facets, it's very clear that a solid face will have higher losses than a polished one. Until now, we just saw the end facets, but we are trying and making some tests to better these facets. So you see how an image where you can see how are the end facets. For the distance, we are also working in which is the optimum distance between the guide and the point where we have to arrive the light. You have also an image. And of course, the geometry of the wafers, okay, is a cross-section, and then, okay, of course, the different dimension, we have to take a compromise with the modal behavior because, okay, change once will change the other, so you have to decide and put one. Okay, and regarding the propagation losses, we have four main parameters. We take care with the absorption, with the roughness, the interface roughness and the wall roughness. We also take care with the stress. and of course, again, with the geometry. So the table, it's, I think I won't take detail about the table, but just for example, tell you that modify one parameter could affect the another one. For example, the absorption, if you remember, on the layer of silicon nitride, we say that there is a high percentage of hydrogen. So the bonds, silicon nitride or nitride hydrogen bonds, absorb the light. So to optimize this problem, we anneal the wafer. So anneal the wafer, crystallize the layer, so then I will have some problems with the crystals that also absorb the light. So just take care with the table and think about the modify one parameter or do some process to optimize some parameter could affect the other one, and then you have also to take a compromise and make the best. Okay, for example, a graph where you can see the different propagation loops that we get in the different fabrication. We start with the test with 6 dB per centimeter, which is a very nice value if it's the first time that we fabricate a component. And on the first MP and on the first multi-project wafer, we reduce it 2 dBs, and for example, from this multi-project wafer, we make 2 tests. One was an etch, and another one was an annealing to improve a little bit the losses. And for example, the etch doesn't change anything, and the losses are almost the same. But doing an anneal, we get a very a lower propagation losses. Okay, the last multi-project wafer measured, it has a value, very nice value, 1.4 dBs. So we hope repeat and maintain or reduce a little bit this value, but I think it's a good value. Okay, to finalize, some images for the different tested. So there you can see the roughness in a wall that makes a lot of losses. So doing an annealing, we can get a very nice waveguide. And some devices images making with different techniques, microscope, optics, electronic, and a loop. So thank you for attending this presentation. It's time to give me some questions.
Okay, thank you very much.
Hi, thank you for your presentation. I have one question. What is the thickest film you can deposit, and how good is the film quality?
In which layer?
I mean the silicon nitride.
Okay, I think the silicon nitride, I can grow a process with 600 nanometers. And I think the homogeneity is also the 5%, like you see now. But I think the problem is that as higher as you grow the silicon nitride, the stress is bigger.
That's why I'm asking. Do you have any process to control the stress, to compensate the stress? Are you working on 6-inch or 8-inch?
No, 4-inch.
4-inch?
Yes, we work with 4-inch wafer, yes.
Okay.
Okay, we measure the stress, and I think we can deposit this layer without very much stress, but the problem is that when we use the stepper photolithography, the stepper equipment use a very, the problem is that to load the wafer has to be very flat. So maybe making photolithography with other techniques,
so
the stress is not, yes.
You have bends, right?
Yes.
Hi. First of all, thanks for your talk. And then I would like to know what are these heaters for, the ones that you fabricate on the chip, and how do you control them? Do you control the temperature somehow, or it is a fixed one?
Okay, I'm sorry, but I cannot answer this question. Okay, I know how to fabricate them. How to control, maybe VLC can answer this question.
Okay. These are thermal tuners. So it's a metal on top that basically you inject a current at it, and it hits the waveguide. So it changes their properties, basically the refractive index. So if you put it in a Mach sender, for instance, you will switch it. Or a ring, you will move the resonance. So that's it. No, it's to change the refractive index locally.
Yeah. How far have you put, do you have to put two heaters to avoid thermal crosstalk between them?
We have different mechanisms to do that. We can use the trenches to avoid to reduce the distance, but 100 microns would be safe.
Okay, then let's thank the speaker again. We need to move to the last talk before the coffee break, and it will be given by Valerio Pruneri from ICFO.
Bien, ¿no? Sí. Vale, vale, perfecto. Okay. Good morning to everyone, and thanks the organizer for inviting me. My name is Valerio Pruneri, and I'm from the Institute of Photonic Sciences in Barcelona. So I'm going to give a talk maybe more material-oriented. We had one question earlier, which was related actually to thermo-optic effect. So you can use thermo-optic effect to change refractive indexes in different materials. And in my talk, basically I'm going to say about two new materials which are not new. Maybe one is more new than the other. And let's say the newest one is graphene. And then there are materials that can be used in optics, which are phase change materials, which people have mainly used in electronics for memories, right? And then the second part of my talk is kind of different from the first part, but I would like to show it to you. Also, some work has been done in collaboration with some local entities here in Valencia, and is about quantum random number generation. So what phase change materials are? Phase change materials are essentially materials that can live in two different states. One is amorphous state, and the other is crystalline phase, right? And you can go from one state to the other by using current, light, and temperature. physically is always temperature that switches from one phase to the other. Yeah? So you can think of phase change materials similarly to quartz and silica, right? So silica is an amorphous material, and quartz is crystalline phase, right? So if you fuse quartz, natural quartz, you get the amorphous phase, which is silica, right? And why phase change materials? Because in electronics they're used because their resistivity, if you want their conductance, conductivity, changes significantly when you go from the amorphous to the crystalline phase. But if you also look in I don't know why my student put photon energy, not wavelength, but so the idea is that if you switch from the amorphous to the crystalline phase, you have big changes in the refractive index in the real part of the chi1 of the dielectric constant, and in the imaginary part, the absorption, right? So if you switch these materials, you can change significantly the refractive index and the absorption. So this is the message. And those are known materials. And so we applied those structures as many people does, also taking into making sure that we take advantage of the resonance, right? So essentially, if you use those materials in a bulk form, the loss would probably be too high, right? And then is what people do. They use evanescent coupling with waveguides, or I will show you other types of structure, plasmonic structures. And the idea that in that case you have a balance between the linear loss and the extra loss or extra phase. When you change the refractive index, you change the phase due to the switching of the phase in these materials. So this is essentially a microring structure in silicon. There is a silica layer as an overclad, and then on the top of that we have some phase change materials, which is very small region. I don't know if you see here, so it's a few tens of microns, right? So this is the region of, no, even less actually, it's 3 by 1.5 micron. So it's a very small region. And still, you appreciate that you can change both the resonant wavelength and the amplitude of the resonance, right? When you switch from amorphous to crystalline and vice versa. And the change is quite significant. You can achieve easily 13 dB modulation in the response at a given wavelength. And the interesting thing is that the process can be also quite fast. Okay? So it's not that fast. I will show you how to switch those material in a much faster way because of the thermal. So because here you involve essentially phonons, right? So you have basically the electrons where the light, basically the electrons are hit by the light, and then you have all the process, the phonons, and together also you don't have only phonons, but you have really a structural rearrangement of the structure. So you're changing the average position of the atoms, right? So you go from amorphous to crystalline phase, and that is a slow process. Yeah? I will show you later that basically without having the structural change, you can still get very high contrast in the optical constants, right? Because those materials, they are high refractive index materials, and since they are high refractive index materials, they also have a high nonlinearity. Yeah? Because the nonlinearity, you know, is proportional to, for example, the chi3, I think it goes like the cube of the refractive index, right? So if you have a high index material, you have high nonlinearity, and you have a high nonlinearity electronic response. So these polarization bonds, which are very significant, and which you might be able to change, as I will show you later. So, I don't know why this doesn't work. Okay, so people This is the only work which is not our work that I will refer to. And people then have thought also to use these materials for switching a reed beam. So when you have a strong pump, you have a 0. Instead, if you don't have the pump, you have the 1 and so forth. So you can really make an optical switching device in a waveguide form and essentially using the concept I've shown in the previous paper, right? So a waveguide where you have some of these materials at the top. Then, of course, you know, you have dielectric waveguides. Then you can think of using basically plasmonic waveguides. So this is a gold wire, right, where we launched light. We couple light by the grating. So it is the propagating plasmon. And then by electrically switching, but at the end I said, you know, it's an electrical pulse, but it's more a thermal effect physically. You can switch the propagation, and you are able to detect a quite significant modulation between the amorphous and the crystalline phase. So, of course, you might tell me, okay, you know, here the question is whether plasmonic structures will be ever used in switching, right? Because they're intrinsically lossy, right? Which is true, by the way. So here we use the plasmonic structure as a linear structure, and then we have our switching device as our switching material on top, right? So, but it shows that given the fact that you can switch with a very small area, I mean, if you shrink the dimension of plasmonics, which is what you want because you go sub-wavelength, then those materials are very suitable and can be combined with plasmonic switching. Another way of combining with plasmonic is to combine with extraordinary transmission. Essentially, extraordinary transmission is an array of holes in a metallic film, right? And again, when you have those materials on top, you can switch the wavelength significantly. For example, here you go from 900 to 1,300 nanometer. So when you go from amorphous to crystalline phase, right? And that's, sorry, when you go from the gold structure to the phase change material, and then when you switch from the amorphous to the crystalline phase, you have an even more significant wavelength shift. So here is a work that we've been doing, and is the concept I was telling you before. If you change the phase, if you change the structure, you're talking about microsecond switch. By the way, everyone is always concerned, the switch is not fast, but there are many applications out there where you don't need fast switching, right? This is, for example, protection and so forth, right? As a scientist, we always tend to say, we want a switch that, you know, doesn't stop light before you are talking about insertion losses, that is fast, that it has a strong modulation and so forth, right? It depends very much on the application, right? Even the modulation depth that you want to achieve really depends on the application, and you will never use, let's say, more expensive devices with, for example, higher extinction ratio if the application requires, let's say, low extinction ratio. So fast and slow really depends on the application. Nevertheless, in this paper, we have shown essentially that without changing phase, we can get very high modulations, right? Very high modulations in very fast ways. So really an electronic response, right? So it's the polarization bond of the material which is changing before actually even the energy is transferred to phonons, right? So vibrations. And eventually this vibration ends up in a structural change, so in the average position change of the atoms. So they're kind of quite interesting material because the changes are significant. So, and then you can make narrow resonance stuff. You can even think of combining with metals to make perfect absorbers, means materials which are very black. This is a picture, right? By the way, of course, I didn't do all this work. My students did this work, and in collaboration with many people. Maybe I'm going to say that this work has been in collaboration with Javier Garcia de Abajo, and the previous one with Simon Wall. And it can always be also narrowband. How do you obtain the narrowband? Well, instead of a single layer of metal, you use 2 layers of metals, right? Because then you have a resonating structure, and you know that every time you have a resonating structure, you have essentially a narrowband operation. So now I'm going to switch material. I'm going to tell you a little bit about the graphene, right? And why graphene is an interesting material, because essentially for us in optics, it gives the possibility of tuning it, right? So essentially you can change its optical properties by applying voltages, right? So you can gate it. And why you can gate it? Because graphene has a carrier density, surface carrier density, which is comparable to the surface density you can achieve with typical breakdown fields, right, of silica. So you can really use microelectronics, FET concept, yes, FET transistors, to change the properties of graphene, right? And again, I'm not, let's say, a fan of graphene on its own, but I'm a fan of graphene when you use it with other materials. For example, here, I think it's a group at Berkeley, used that in combination with silicon waveguides, and they show a quite nice modulation. This is, I think, is a NICFO work, where they show that you can create perfect absorbers that you can tune. This work, I'm not sure who it is, but it's with plasmonics. And this work is our work on plasmonics with graphene, where we show that you can tune the material. So, and then how you can combine it to make integrated optics device. Well, this is a very general concept, which is done with a Fabry-Perot structure, but you can very well translate this concept with microrings, with any resonance structure. And the idea is that essentially the graphene is a very thin material, is 1 atom thick. So you're talking about 0.3 nanometer. The absorption is not that high, it's 2.3%. But if you go to Pauli blocking, means that you fill in enough electrons or holes so that you forbid the transition, then it becomes perfectly transparent, right? And in that case, then this 2.3% modulation gives you a certain degree of freedom, because if you put that in a resonating structure, you understand that the light, the photons, go through it many times, and then the final effect can be significant, as it is shown here. So you can have a very significant modulation. So even though on its own doesn't have a significant absorption, which is also the beauty of graphene, for many applications, this absorption can be modulated, and you can take advantage of this effect, right? And you can also think of combining this with other type of resonance structures. In this case, we are still trying to make basically a window which is transparent for most of the wavelengths, so and scatters red and green and blue, right? So the idea is to have a window that you address with red and green and blue laser, and those wavelengths are scattered from the surface. Yeah? But at the same time, the resonance scattering is so narrow that the eye doesn't perceive that there are these resonances. So it's really like you have to imagine a transparent projection display. So this is kind of the application we are thinking of. But again, you can translate this into plasmonic structures and modulate those structures. So in proximity of resonances, graphene can work very well. This is the message. I'm changing completely topic, and I will speed up a little bit. So this is a work which has been done also with VLC Photonics and with València University, and also a group in Milan that is led by a friend of mine that studied with me, actually. And basically what we are trying to do here is, again, switch your mind because it's totally different. This is hardcore photonics. So, you know, people are very interested in random numbers. So random numbers are everywhere, right? I don't want to be a philosopher. Our life is also random, maybe, I don't know. But for somebody it's more random than others, but okay. So random numbers are everywhere. So typically random numbers are generated through computers, right? So there are programs that generate those random numbers. And those programs are basically produce what are called pseudo-random numbers, right? And if you wait long enough, you have to wait long enough, you would see patterns. So essentially, at some point, they're not random anymore, because you will find numbers, you will find correlations between all these numbers, right? And this is kind of a problem in security, as well as, for example, in big computer simulations. Imagine you want to simulate a nuclear reaction, right? You know, in nuclear reactions you have neutrons. You have to slow down neutrons so that they're absorbed by the nuclei. And it's always a question of randomness, whether the neutron is absorbed, is scattered, and eventually the neutron that is absorbed produces fission, right? They slow down the neutrons because the cross-section increases of the interaction, right? But still you don't know whether the neutron is absorbed, is scattered, or when it's absorbed, gives fission, right? And those kind of things then are very important, even biological simulations, right? And then the other way of generating random numbers is a physical way. So, and then there is an Intel product which uses thermal noise, right? So you've got a transistor, essentially you pick up the noise, which is thermal noise, and you can make randomness out of it. Still, people found out that this is not truly random, right? And then there is another part of physics, which is quantum, which is intrinsically random, right? So we cannot prove that is a principle. So, you know, by principle, quantum is the most random things that exist, right? So initially people then say, okay, then I take a photon, a single photon, I put a beam splitter, right? And when the photon hits the beam splitter, I have 50% chance that the photon is transmitted and 50% chance that the photon is reflected. Yep. So then I can make a random number generator. Yeah. But then you need what? Single photon detectors. You have a single photon regime, which means that you cannot produce many bits per second, right? And you have an expensive device. Yeah, especially if you want to use now superconductive single photon detectors, which works at cryogenic temperature. Here is a totally different scheme, what I'm going to show. So our scheme is it uses classical hardware, so components that you buy off the shelves, so classical components used in a quantum manner. When I say in a quantum manner, it's because a laser, you know, has two parts. Right? First of all, a laser has a spontaneous emission, which is everywhere in this room, vacuum fluctuations. And a laser also has a stimulated emission, right? So that's why it's laser, light amplification by stimulated emission of radiation, right? So as long as you increase the current, for example, of a diode high enough, you go above threshold, and then you take these spontaneous emission photons and you bring them above threshold. So you go from a microscopic state, let's say, to a macroscopic one, right? And the beauty of this is that when you do that, the phase of the light, the stimulated emitted light, is the same as the phase of the spontaneous emission light, right? But the phase of the spontaneous emission light is a vacuum fluctuation and is not determined. Well, in fact, people say it's not determined if the cavity is infinitive. It doesn't exist, of course. You know, the cavity that we make with the mirrors and so forth is limited in space, but still is not determined, right? So every time I pulse my current of the laser above threshold and below threshold, and if I stay below threshold long enough that the stimulated emission photons, which were generated in the previous pulse decay, leave the cavity, then when I repulse, when I generate a new stimulated emission pulse, the phase is random. So in this way, I generate a train of pulses with random phase, right? Where is the quantum effect? The quantum effect is in the phase due to the spontaneous emission. So I have a quantum train of pulses with random phase. Now, if I delay one, I split these pulses and I delay one with respect to the other and I make an interference, I have a random distribution. And you see it here also with the correlations, right? So, and I'm using completely let's say hardware, I mean commercially available components, which are not essentially single photon and quite expensive components, right? So that's the beauty. So these devices were made at ICFO, right, by my group and Morgan Mitchell group. We made those devices, and then, I don't know if you have heard, they were shipped essentially somewhere else for some important experiments. So this is one experiment done by Delft, so to prove that Einstein essentially was wrong, yeah, because they basically closed the loops and they did Bell inequality experiments. And the quantum random number generator basically is the dice, is the device that was starting the whole process, right? And it's kind of weird, right? No, because also when you talk about cryptography people, they talk about secure communication, and then it's counterintuitive because they say, oh, bloody hell, how can it be secure if I use random numbers, you know? But that's the beauty of quantum mechanics, right? So you can still find secure protocols by using random numbers. And also, we shipped a device to NIST, NIST in the United States, and another one to Vienna, the quantum computing group in Vienna, and they all made these, let's say, breakthrough experiments that the people were looking for a long time, quite fundamental experiments. So now, where we are, now we want to integrate that, the concept, right? And so with VLC, we have, this is one of the schemes that you can use. So in integrated optics, it would be difficult to have, you know, because I told you that you've got to stay below threshold long enough, right, to forget the stimulated emission photons that you have generated in the previous pulse. And this gives you a limit in the repetition rate of the laser. That means that if I make an interferometer with a delay, the delay has to be long. And this long delay might be difficult in integrated optics. I don't know, maybe you have some ideas. I've seen some talks this morning. I would be happy to discuss them with you. And then what we say, okay, but let's use another concept which is widely used, which is to take a reference oscillator, so continuous wave laser, and beat two lasers. It's exactly the same, essentially. It's exactly the same. The only difference is that you will have a bit in frequency, and then if you sample that bit signal at a specific time, that bit signal will arrive with a different phase delay any time, because the phase delay will depend on the initial phase of the two lasers. The continuous wave laser will always have the same phase, but the laser that I'm pulsing will change its phase, as I described earlier. Yeah, and this is the way we did this interferometry bitting on a chip.